We can think about two different types of systems. The first type is finite impulse response systems, and the second type is infinite impulse response systems. So finite impulse response systems, the term is abbreviated as FIR, and infinite impulse response is abbreviated as IIR. A finite impulse response system, as the name suggests, has an impulse response which has a finite support. That is, the impulse response has non-zero values only at a finite interval of lags. Whereas for an infinite impulse response system, the impulse response has an infinite time support, which means it has values from for time indices from minus infinity to infinity. Now, recursive systems are those systems which use a combination of their inputs and outputs to generate the next sample of their outputs. So the response of a recursive system has two parts. The zero input response, that is the response of the system when its input is zero but when it has a non-zero state vector, and the zero state response where the internal state of the filter, internal state of the system is zero. So let's consider a recursive system whose difference equation is given as y of n is equal to a y of n minus 1 plus x of n. This is a recursive system because it's using its output as an input as well, while it's calculating its output. Okay, so let's analyze what is going on in here. So let's write the response more explicitly. So what is y0? y0 is a times y minus 1 plus x0, right? So that is quite simple. And let's write y1. That is a times y minus 1, sorry, a times y0 plus x1, which is equal to a times y minus 1 plus x0 plus x1, which again is then equal to a squared y minus 1 plus a x0 plus x1. So if you continue writing the output of the system, you're going to end up with y of n equals to a to the power n plus 1, y of minus 1 plus k from 0 to n, a to the power k, x of n minus k. Now, this is nice, so let me just make it a little bigger, perhaps, okay? So we can define two parts in here. One part which depends on y only, the previous values, actually one previous value of y only, that is this part. Oops, sorry, I was going to just write it here. So this part. And the second part is the part which depends on the input values of the input. So let me just use another color, maybe green or kind of darker green perhaps. Yeah, okay. So the second part is this part. Okay, anyway, it doesn't matter the color. Okay, so if the input is 0, that is, if all values of x are 0, the output of the system is this first part, and that is going to depend on the state of the system at time n equals to -1. That is, whatever value the system was storing at y -1, at time instance -1, is going to form the output of the system. So this part then is the zero input response, zero input response, and the second part is the zero state response. So why is it called a zero state response? The response depends only on the values of its input, the system's input, and whenever the state of the filter at n equals to -1 is 0, we're going to have this response. So that means we can just express this difference equation in here as y 0 input of n, which is the first part, plus y 0 state of n. Okay, so we're going to see later that we can express, or we can work with the transient responses of systems by using this expression, or these expressions, which will be useful later on, but not today. Okay, so our next topic is cross-correlation. Now, cross-correlation is a measure of the relatedness of two signals, and it shows at which lags the two signals are similar. So let's say we have a signal x and a signal y. The cross-correlation of these two signals is defined as in this equation. Okay, so we shift y by n samples and multiply it by the value of x at that same lag, and we end up with our xy, which is a function of lag. So L is the lag in here. Oops. So it's the lag. And importantly, L is equal to 0 or plus minus 1 or plus minus 2, etc. So it is an integer. Okay, so cross-correlation then is a function of lag L, and not time itself. So it's not a function of n, but it's a function of L. So how about if you get the same two signals, but switch the order? So instead of our xy of n, the cross-correlation of x with y, now we have cross-correlation of y with x. And if you write the cross-correlation of y with x in the same format, we end up with an interesting relation. So just comparing these two, we can tell that our xy of L is equal to our yx of minus L. Okay, so what else? We can also say that, okay, so I'm just going to delete parts of it. Okay. I'm just going to move this a little bit to the side so I can write stuff here. Okay, so that is one important thing. So let me just mark it as 1. And another property of cross correlation is that our xy of L is the convolution of x of L with y of minus L. And here we used, again, the property or the definition of convolution sum. So let me just write it here once again. It is simple, but let's just write it once again. So x of n convolved with y of n is equal to, I'm going to write it down here, sum over all k, x of k, y of n minus k. Okay, so by that relation, we can just define the cross correlation as the convolution of x of L and y of minus L. Okay, so that's good. And again, cross correlation is going to show at which delays the two signals are similar. And we're going to use cross correlation while we're designing optimal filters. So it is a very important sequence. Okay, so what if we select the second signal y of n as the same as the first signal x of n? Then we end up with autocorrelation, that is the self-similarity of a signal. And just by using the definition, our xx of L is equal to x of n minus L summed over all n, which is equal to x of n xn plus L from our earlier derivation. And we end up with our xx of L equals to our xx of minus L. So this again is, let me just write it once again, it is the self-similarity of a signal. Okay, so let's have a look at some properties of cross and autocorrelation. So cross correlation of two signals is equal to at most the geometric mean of the energies of the two signals. So sorry about the little typo here, it's not geometric, obviously it's geometric. So here should have been an O. Yep, okay. So let's get an energy signal, m of n equals to ax of n plus by of n minus L, such that the energy of this signal is greater than 0 and less than infinity, right? It's an energy signal. And let's also assume that A and B are non-zero. So let's write the energy of the signal M. So energy of M is equal to, for all n, we're going to add mn squared, absolute squared. Now that is equal to, again for all n, ax of n plus by of n minus L squared. By the way, we're assuming that our signals are real valued, so we can do this operation. So we can go from the sum, the square of the signal to absolute value squared of the signal quite easily. Now let's write what this is. So we have a squared, the autocorrelation of x at 0 lag, okay, plus b squared, the autocorrelation of y at 0 lag, plus 2ab cross correlation of x and y at a lag L. Now we know that our signal is an energy signal, which means this quantity will be greater than 0. We have defined it before, right? And let's parameterize this by dividing everything by b squared. So we would like to, just parameterize the second part. So let's just divide everywhere by b squared, so that we have a squared over b squared rxx 0 plus ryy0 plus 2a over b rxy L, which again is greater than 0. Now we are going to use a parameter, if you like. So let's define P as A over B. Then the expression that we have derived above becomes P squared rxx0 plus ryy0 plus 2p rxy L. And we would like this to be greater than 0. Now you can see that this is a polynomial in P. So this is a polynomial in P. Now, for a polynomial to be always greater than 0, and this is a second order polynomial, we should have no roots, right? No double roots and no real roots, sorry. So if you wanted to have a look, we would have something which looks like this, a second order polynomial in P. So no roots, no real roots. So no real roots. This is something very basic that we already know, right? So following on from there, we can just write the determinant. And if you remember from high school maths or first year maths, we know that for a polynomial to have no real roots, its determinant should be less than 0. So when we write the determinant by using rxx, ryy, and rpx as our polynomial coefficients, we have this relation. So delta equals to 4rxy squared L minus 4rxx0 ryy0. That should be less than 0. And Well, in fact, it's going to be less than or equal to 0. When it's equal to 0, we're going to have a double root at 0, etc. And, we can have the same sort of reasoning in here if we allow changing these to include equality as well. Okay, what else? What do we know about this? So I'm just gonna clear the second part because I've forgotten something which is pretty important, and that is the identification of the autocorrelation at zero lag and autocorrelation at autocorrelation of x at zero lag and autocorrelation of y at zero lag as the energy, right? So if we set L to 0, we're going to have energy. So then that means this is equal to 4rxy squared L minus 4 energy of x, energy of y should be less than or equal to 0. Then that's going to mean the cross correlation of x and y at the lag L is less than or equal to square root of energy x and energy y, which means the cross correlation of two signals at any given lag L is always going to be less than the geometric mean of the two energies of these signals. Okay, so that is good. So what happens if we select x of n as y of n, which means we have autocorrelation? In that case, the autocorrelation at any lag will be less than or equal to the energy of x, and energy of x is equal to rxx0, that is the autocorrelation at zero lag, which means the autocorrelation at any lag L is less than the autocorrelation at L equals to 0. So let me just write that result here. The autocorrelation of any lag L is less than or equal to the value of the autocorrelation at zero lag. L equals to 0. Okay, so that is also an important result. The autocorrelation sequence will have its maximum at zero lag. So the signal is maximally correlated with itself for an energy signal. Now, we can normalize then the autocorrelation with the value of the autocorrelation at zero lag and the cross correlation. I'm sorry about the second part, so this should have been xy and this should have been xy as well. I'm sorry about this little typo here. So we can normalize the auto and cross correlations with respect to the maximum values that they can achieve. And as a result, we end up with normalized auto and cross correlations, which are always, whose absolute values are always less than or equal to 1. So if it's -1 or close to -1, these signals will be negatively correlated. And if it's +1, they're positively correlated. And if it's 0, then they're uncorrelated. What would mean if the cross correlation of two signals or an autocorrelation of a signal with a given lag is 0, that means the signal, well, the two signals which go into this equation will be uncorrelated. Okay, so let me just write this down as a little note then. If rho xy L is 0 for all L, then X and Y are uncorrelated signals. Okay, so that's also an important result. And let's now consider a signal which is corrupted by additive noise. So we have a signal X of n, and we add a noise W of n to that, and we obtain Y of n as a result. That is, we have Y of n equals to X of n plus W of n. Here, X of n is signal, and okay, signal. Typically, it's going to be the signal of interest that we want to, say, denoise or obtain back, and W of n is the additive noise. Okay, so this is our signal. And if you look at the autocorrelation of Y, our YY of L is equal to, for all n, Y of n, Y of n minus L, which is going to be equal to the autocorrelation of X at the leg L plus the autocorrelation of W at the same leg plus the cross correlation of W with X plus the cross correlation of X with W, all at the same leg. Now remember what we said before. If the two signals are uncorrelated, then their cross correlation will be 0. So let's write it here. If W of n and X of n are uncorrelated, then our Wx L is equal to our xw of L equals to 0. Now we will see towards the end of this course that this relation is very important. It allows us to do many different things, including adaptive filtering, including optimal filters, etc. So it is very important to know about uncorrelated signals. So then what happens if we process a signal via a linear time invariant system and obtain an output, and we look at the cross correlation of the input and output? We end up with input-output correlation sequences. So we know that if we have such a system, the output Y of n is equal to X of n convolved with H of n, right? So let's have a look at the correlation of input and output. So the first one is our xy of L, which is X of L convolved with Y of minus L, which is equal to X of L convolved with X of minus L convolved with H of minus L. which is equal to the autocorrelation of the signal X at a lag L convolved with H at a lag minus L. So yeah, time reversed version of L rather. Okay, so that is the first property about correlation of input and output. So you feed a signal X of n into your linear time invariant system and you obtain Y of n, and the cross correlation of the input and output depends on the autocorrelation of the input sequence convolved with whatever system you have in the middle. And secondly, our Yx of L is Y of L convolved with X of minus L, which is equal to H of L convolved with X of L convolved with X of minus L, which is the same thing as H of L convolved with our XX of L. So two things which are basically the same. So that's good, input-output correlations. And what about the autocorrelation of the output then? Okay, so the autocorrelation of the output. Then we're dealing with our YY of L, which is Y of L convolved with Y of minus L, which is equal to H of L convolved with X of L convolved with X of minus L convolved with H of minus L, which gives us the convolution of the autocorrelation of the input signal with the autocorrelation of the impulse response of the system. So that means if we have a signal that we input to a system which has an autocorrelation of Rxx of L, and we have a system, a linear time invariant system, H of n, the output autocorrelation will be equal to Rxx of L, the input autocorrelation sequence convolved with the autocorrelation of the system. Okay, so let's make it a little bigger. Okay, that's good. So that concludes this video, and we're going to have a question which follows up this video. So I'm going to ask you to answer that simple question and submit your solution via Auth2Class, which will serve as an attendance for this course as well, although attendance is not part of the grade. So please do submit your responses in time. Thank you, and see you in our next video.